Let's say a local shop has 5 flavors of ice cream, and you want a cone of 3 scoops of different flavors. How many different types of cones could you get? Let's start off by going over combinations and permutations. Both are ways of counting up how many ways you can choose objects from a set of options. With combinations, the order of your choices doesn't matter, but with permutations, the order does matter. Suppose you are at an ice cream parlor and you are choosing the flavors you want. If you order a milkshake, then it doesn't matter in what order you pick the flavors, since they all get mixed together anyway. That's a combination. But if you order an ice cream cone, then the flavors can be stacked one on top of the other in different orders. That's a permutation. Combinations are written with a big C. On the left side of the C, there is a number n that tells how many total options we have to pick from. On the right side, a number r tells us how many to choose. If you have n objects and take them r at a time, NCR is the number of combinations. Permutations are written the same way, except with a big P instead. If you have n objects and take r of them in a particular order, NPR is the number of permutations. But how do we calculate combinations and permutations? Let's dive right in with an example. Evaluate 5p3. 5p3 represents the number of permutations when we have 5 objects and take 3 of them in a particular order. To evaluate this number, it may help to think of it as ice cream scoops. In our example, we have 5 flavors of ice cream to choose from, and we're choosing 3 scoops for the cone. Let's also assume that the flavor can't be used more than once. We want to have 3 different flavors. Order matters in this case because a cone with vanilla as the bottom scoop, chocolate as the middle scoop, and strawberry as the top scoop will be different from a cone with strawberry on the bottom, chocolate in the middle, and vanilla on top. So let's start at the bottom. For this problem, we have 5 flavors to choose from for the bottom scoop. Let's pick chocolate to illustrate this. Once we've chosen the first scoop, we now only have 4 scoops to choose from for the middle scoop. And finally, 3 scoops to choose from for the top. So after we make a choice, we have 1 fewer option for the next selection. Again, for this problem, we have 5 choices for the bottom scoop, 4 choices for the middle scoop, and 3 choices for the top scoop. We can use the counting principle to figure out the total number of different ice cream cones by multiplying. 5 times 4 times 3 equals 60. So 5p3 equals 60. That's a lot of cones. Since all permutation problems are solved in the same way but with different numbers, we can take the solution process we just used and make it into a formula. Here is the formula for permutations. NPR equals n factorial divided by n minus r factorial. To evaluate a factorial, multiply all the whole numbers between 1 and the given number. To see how this formula works, let's use it to solve the same ice cream cone problem as before. In our formula, n is the total number of choices, so n equals 5. And we're choosing 3 scoops out of 5, so r equals 3. Plugging these values into the formula, we get 5p3 equals 5 factorial over 5 minus 3 factorial. Let's simplify the denominator, so we get 5 factorial over 2 factorial. Now, let's expand the numerator and denominator. 5 factorial is 5 times 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. We can simplify the fraction a bit by canceling out factors. Notice the product 2 times 1 is in both the numerator and the denominator, so we can cancel these factors. The factors that are left in the numerator are 5 times 4 times 3, and that's how we solved the problem the first time. We had 5 flavor options for our first scoop, 4 for the second, and 3 for the third. So we found 5 times 4 times 3, which equals 60. The formula for permutations is just a different way of writing the same product using factorials. You write a factorial with the total number of options in the numerator. In this case, that was 5 factorial. Then, depending on how many choices you need to make, you divide out the factors you don't need, using another factorial in the denominator. In this case, we only needed to make 3 choices, so we divided away the last 2 factors we didn't need. Great! Now let's look at a problem that involves combinations. Let's find 7C4. 7C4 represents the number of combinations when you have 7 objects and take 4 of them. To help us think this through, let's imagine we have 7 donuts and we're choosing 4 of them to put in a basket to bring on a picnic. In this case, order doesn't matter. Each donut that is selected is put in a basket. Let's calculate the number of ways of choosing 4 donuts out of 7. We have 7 donut varieties for our first choice, then 6 donut varieties for our second choice, 5 donut varieties for our third choice, and 4 donut varieties for our last choice. Wait just a minute. This looks like the same thing that we did for permutations. And so far, it is the same. But let's think about this a bit more. In this example, we chose the chocolate glazed pink donut first, followed by the chocolate sprinkled donut, the blue donut, then the green donut. But the basket will end up being the same if we change the order of how we selected the donuts. We could have selected the green donut first, the blue donut second, the chocolate sprinkled donut third, and the chocolate glazed pink donut last. And we don't want to count these baskets as 2 different baskets, so we need to divide out the repeats, or the redundancies. But how many repeats are there? Every time we choose 4 donuts, the repeats include all of the ways of reordering those same donuts. That's 4 times 3 times 2 times 1, or 4 factorial ways. This means that every single donut combination belongs to a group with 4 factorial redundancies. We can divide our total, 7 times 6 times 5 times 4, by 4 times 3 times 2 times 1, and account for any repeats. Now, we can do a little bit of canceling to simplify our fraction. There's a 4 in the numerator and the denominator, so these can cancel out. 7 times 6 times 5 is 210, and 3 times 2 times 1 is 6. 210 over 6 is 35, so our answer is 35. So there are 35 different combinations of donuts we can put in the basket. The solution process we just used can also be written as a formula. Let's try this problem again using the formula for calculating combinations. NCR equals n factorial divided by n minus r factorial times r factorial. Now let's apply the formula to calculate 7C4. The total number of objects is 7, so n equals 7. We're choosing 4 objects, so r equals 4. Now we can plug these values into the formula. The numerator is n factorial, so we have 7 factorial. In the denominator, we have 7 minus 4 factorial times 4 factorial. Simplifying the denominator a bit, 7 minus 4 equals 3, so our denominator becomes 3 factorial times 4 factorial. In this expression, the 7 factorial on the top shows we are rearranging a total of 7 donuts. The 3 factorial in the denominator shows that we are eliminating 3 of those 7 donuts because we only want to put 4 donuts in our basket. The 4 factorial divides out the repeats since the order of the 4 donuts we're choosing doesn't matter. If we expand our factorials, we have 7 times 6 times 5 times 4 times 3 times 2 times 1, and 3 times 2 times 1 times 4 times 3 times 2 times 1. Notice we have 4 times 3 times 2 times 1 in both the numerator and the denominator, so we can cancel out those factors. Just like last time, we have 7 times 6 times 5, which is 210, and 3 times 2 times 1, which is 6. 210 divided by 6 is 35. Great, this is exactly the answer we got before. There are 35 different combinations of donuts we can put in the basket. Awesome job finding combinations and permutations. So the next time you order a triple ice cream cone or pack a basket full of donuts, you'll realize just how many different ways of doing that there are.